Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. My name is Nur Afin Aina binti Ahmad Razani and we are presenting our project title Flash Design to Separate Pentane and Hexane under the course of SATG 2433 Chemical Engineering Thermodynamics, and our lecturer is Prof. Madya TS, Dr. Nurhaniza binti Yusof, and we are from group 5. So for our group, we have 5 team members, which include myself, Vishnavi, Izzatun Najla, Nur Ain Natra, and also Alisa Aisha.
Good day everyone, my name is Vaishnavi Gunasekre. Along with my group members today, we are presenting our thermodynamics project on the flash separation of a pentane hexane mixture. Flash separation is a vapor-liquid equilibrium process commonly used in chemical engineering to separate liquid mixtures based on differences in totality. In this study, we analyze how pentane and hexane behave under specified operating conditions using thermodynamic principles. The main objective is to understand phase behavior and separation performance of the system. Next, we make several assumptions to simplify the analysis. We assume that the system is operating at a steady state with no accumulation in the flash drum. The mixture consists only of pentane and also hexane, and the vapor-liquid phase are in equilibrium. The vapor phase behaves as an ideal gas while the liquid phase is treated as an ideal solution. Based on these assumptions, Raoult law is applied for the VLE calculation. We also assume there's no heat loss to the surroundings and negligible changes in kinetic and potential energy. Here, I have attached the table of operating conditions used in this study. The feed consists of an equal molar composition of pentane and also hexane. The system is operated at an atmospheric pressure of 101.3 kPa and a temperature of 50 degrees Celsius. The temperature lies between the boiling points of the pentane and hexane, which ensures that both vapor and liquid phases are present during the flash process, making separation possible.
So based on the introduction, we also stated the operating condition for this system. So here are the block diagram for the flash distillation column and also the entire table B.2 where we will use this for calculation later. Okay, so here, for the first thing to do when we want to separate the mixture, so we have the component pentane and hexane here. So in this table, we are extracting the data of A, B, and C value for these components. Okay, so for the step one is to calculate the PI set using the Anton equation. So to get the P pentane set and also P hexane set, so here are the data. So step 2, to calculate the bubble point, PB, so the initial assumption that we put is L, the liquid fraction, is equals to 1, and also the XI equals to 1. So the calculated PB value, we get 106.842 kPa.
In step 3, we will calculate the dew point. So we assume the vapor fraction equals to 1, which means the mixture is completely in vapor phase. Therefore, the vapor composition Y is equals to the overall composition, which is Z. So using the dew point equation, we will substitute the mole fraction of pentane and hexane, which is, we assume it 0.5. So Y will be divided by the summation of mole fraction over P saturated that is obtained from the Antoine equation. So after the calculation, we obtain a dew point pressure of 80.815 kPa. So since our operating pressure 101.3 kPa lie between the dew point pressure and the bubble point pressure, so that means the system is in the two-phase regions, meaning both liquid and vapor are present simultaneously. In step 4, we will find the K value. So the K value is defined as the ratio of the vapor mole fraction divided by liquid mole fraction. And it can also be calculated using K equals to P saturated over operating pressure, which is 101.3 kPa, which originally comes from the equation above, which is the mole fraction of vapor multiplied by the pressure equals to mole fraction of liquid multiplied by P saturated. So for pentane, the K we obtain is 1.575, and for hexane, the K that we obtain is 0.534. So this K value will be used in the next step to calculate the moles of liquid and vapor.
So next, I will explain the step 5 of our flash distillation calculation. In step 5, Firstly, we calculated the amount of vapor produced during flash separation process using the Rashford-Rice equation. So this equation is used to determine how much of feed mixture vaporized at the equilibrium condition. We substitute the feed composition, which is 0.5 for both pentane and hexane, and together with their K value we obtain from the previous step. So after solving the equation, we obtain the vapor amount V is equal to 0.203 mole. This means that about 20.3% of the feed mixture vaporized during the flash distillation process. This occurs because the pentane is more volatile than hexane, and therefore it tends to enter the vapor phase more easily. And then we calculated the amount of liquid remaining after the separation. Using the overall material balance and assuming a feed basis of 1 mole, we subtract the vapor amount from the total feed. So therefore, liquid amount L is equal to 1 minus 0.203, which gives us 0.797 mole. This result shows that approximately 79.7% of feed remaining in the liquid phase, while 20.3% will becoming vapor. So this value confirms the phase distribution of the pentane hexane mixture under the specific operating condition. Thank you.
So now I'm going to explain about how to find the liquid vapor phase mole fraction. So for liquid phase mole fraction, we assume Yi equal to Zi, meaning that the composition of the vapor phase is equal to the total feed composition. And then we use this equation to find and add pentane. Z pentane equal divide 1 plus V K pentane minus 1. We can use V vapor, mole of vapor, because we make assumption of Yi equal to Zi just now. So we substitute the value that we have. So we got X pentane is equal to 0.448. So to find an X for hexane, we just minus 1 minus 0.448 and we got 0.552. So for vapor phase mole fraction, we use the same formula, but for Y pentane, the Z pentane need to multiply with K pentane, divide with 1 plus V K pentane minus 1, and then we substitute the value, then we got 0.705 for Y pentane, and for hexane we use the same formula as well. So we got, after substitute the value, we got Y hexane 0.295.
Finally, the thermodynamic analysis of this pentane and hexane binary mixture successfully demonstrated the principles of flash separation under the specified operating conditions. By assuming ideal solution behavior and applying Rawls' law, we are able to analyze the phase equilibrium of the system. At 50 degrees Celsius, the calculated bubble point pressure of 106.842 kPa and dew point pressure of 80.815 kPa confirm that the system lies within the two-phase region at 101.3 kPa, meaning both vapor and liquid phases are formed. From the results, we can clearly observe the effect of relative volatility. Pentane, being the more volatile component, is enriched in the vapor phase with a mole fraction of 0.705 compared to its feed composition of 0.50. Meanwhile, hexane concentrates more in the liquid phase. In terms of separation performance, for every 1 mole of feed, approximately 0.203 moles of vapor and 0.797 moles of liquid are produced. Overall, this shows that the flash separation is an effective method for separating components based on materiality differences, and the results align well with thermodynamic principles. Thank you.